Jeremy, I put that with a pogo stick.
Yeah, and I well, you can find those anywhere. Yeah.
Yeah.
Fantastic. Jeremy, I have a question. Yeah. Yeah. It's a sense of it. Yes. I'm kind of busy right now.
So because the camera's here, you have to, if you're gonna be on the YouTube, you have to stand here.
Okay.
You can't stand back there.
All right.
Okay, so you can either use that to, well, just basically be here once in a while, at least, so somebody doesn't miss usually.
Oh, okay.
And this is the goes the opposite.
Are you able to get my slides that I sent?
Actually, Jeremy has them. He said, you're good with that to car slides, right? You load-
Yeah, I have the file. I'll come up and set it.
Okay.
I have like 2 videos in there. Will they like play?
Is there sound?
No, it sounds fun.
The video should be fine.
Video-
If we have any issues, we'll troubleshoot it.
Okay.
You might have to click inside the video to make it work.
I have it on auto.
All right. Sometimes that you do have to click it to make it.
Thanks.
Make sure we're not muted. Got anything weird with the audio? All right, good. Oh, so we need to share the screen. That's the other thing I need to do. Right.
Hello, everyone. If everyone could take their seats, we can get started. So welcome, everybody, to the June meeting of the DVAA. Welcome, everyone here in the room and all of you hanging out there on YouTube. We have a great meeting for you tonight, so we're really happy you're here. Thought we'd start out celebrating the Vera C. Rubin Observatory. Maybe you haven't heard too much about this, but it is going to be, they're going to be live streaming the first images on Monday, the 23rd. So you can check out this website, rubinobservatory.org. This is a scope. It's located on a mountaintop in Chile. And it will be over 10 years. It's going to spend 10 years creating repeatedly scanning the whole sky. It is reportedly the biggest camera ever built. So it's going to give us a view of the sky that we haven't had with any other instrument. Could be really cool. So check it out there on Monday, the 23rd at 11 o'clock. Okay, now I know this is what you've all been waiting for. I'm going to give you a little bit of a flavor of some of the stuff we learned in the membership survey that many of you participated in. And thank you, by the way, for everyone that participated in our membership survey. We did this because we thought we hadn't done it for about 5 years. And we'd like to know how things are going for people, what you'd like, what additional things you'd like to do, what's not working out for you. And that's what the survey was intended to do. So who answered the survey? Well, 50 people, which is about a fifth of the membership. Not too bad. Interestingly, we have a lot of new members in this survey. So if you add together 20% and 15%, so almost 40% of the people that responded to the survey have joined within the last 3 years. So I thought that was great because we're then getting a sample of newer members. Interestingly, 60% of them are over age 65. Yeah. We're going to talk a little bit more about that in a minute. A fifth of them were female. And we have a lot of people that retired. About 50% were retired, completely retired, and then another 20% retired, but doing some work or consulting.
Tethered.
It's tethered, all right. Well, hopefully I didn't put too much down in that corner. All right. So back when we did this survey before, in 2018, we had a lot fewer people that were, it's okay, Jerry. Perfect.
Just remember first. Magic piece of.
Back in 2018, we had, the way this is the light blue is the current survey and the dark blue is 2018. We had, as I said, about 40% of the people this year had joined within the last 3 years. And this year, or last, in 2018, that was about half. So about 20% of the people. So we have many, many more newer members that are responding to this survey. But interestingly, as you saw, we have a lot of people that are over age 55, and that's greater than it was in 2018. Now, there's a kind of been a mystique that I think a lot of you see written about, that back in the 80s, when a lot of astronomy equipment was becoming cheaper, more accessible to people, you had a lot of people joining the hobby. And many of those people have aged, and we get to the point where many of them are older, and we need to redouble our efforts to bring younger people into the hobby. However, what I hear anecdotally a lot is when I hear, well, what brought you to DVAA? People say, well, my kids went off to college, or I'm retired, and now I have time to do it. And so I think that is really what we're seeing here. I think what this is showing us is that astronomy is such a time-intensive and resource-intensive hobby that many people get to the stage of their life where they can give that time to a hobby rather than taking their kids to hockey games, soccer games, whatever. Then they're at the time of their life when they can devote themselves to a hobby that they enjoy. And I think that's what we're seeing. So I absolutely think we need to embrace that. We have a lot of new people who are nevertheless in a later stage of their life, but are for the first time discovering astronomy. And that's pretty cool. When we asked, how did you first learn about DVAA? Not too surprising, it's usually through the internet. I like this one. Everybody said DVAA was good value. Pretty much communication with members was pretty good. And most people felt we were doing enough for new members, although there are some people here, about a little less than a fifth, that said, no, we need to do more for new members. And when we get into the comments, we'll learn a lot more about that. I think we're doing a pretty good job letting people know about the benefits that the club offers. The telescope rentals, the messaging group, the website sections, the clinics. What we're not doing as good a job at is letting people know about the what's offered by the Astronomical League. So all these things that are a little bit lower on the recognition scale, that's the Reflector Quarterly Magazine, which is a Astronomical League publication. The magazine discounts you can get off on Sky and Telescope and Astronomy if you are a member of a club. And then the certificates that you get for observing. So there's room for improvement there. We'll definitely work on that. Now, which DVAA membership benefits do people like the most? They like the forum. They like the website. They like the clinics, indoor and outdoor. So those were the most popular things, not surprisingly, that people liked about the club. We also asked which DVAA events have you attended in the last year? And the most popular was the public star parties at Valley Forge. So something like 75% of members have come to at least one Valley Forge star party in the last 2 years. Close to 70% have come to a meeting, this meeting in person, a monthly meeting, or attended on YouTube or watched it, the recorded version. So those are the most frequent events. But of course, we have a lot of other things to do, which that's not surprising because many of these things, the clinics, the outreach and trips, they appeal to a smaller segment of the membership, and that's just fine. Okay, so that's all for the survey. Next week or next month, we'll go into the rest of the survey, talk about whether people like the monthly meetings, what kind of training you'd like, how to attract more people of a diverse nature to the membership, how to improve the club, and your comments. Okay, so in June, we have a lot of overnight star parties to talk about. It's going to be we better have good weather this weekend. Look at this. A lot of star parties going on. Of course, I'm sure they'll have good weather out in Bryce for the Astronomical League convention, but the Cherry String Star Party is the first one. Registration's closed for that, but at least one person did get their registration in, so we'll wait to hear how that goes. There are 3 semi-local, regional anyway, overnight star parties. And if you've never been to an overnight star party, I urge you to consider going to one of these. It's a good chance to, in a relaxed setting, talk to other people in the hobby. It's not just our club, it'll be lots of other clubs. And so it gives you a view that you don't get if we just talk to each other. The Green Bank Star Quest is about 7 hours away. I've been there, Jeremy's been there, so if you'd like to know more about that, talk to either one of us. You do not need, they have advanced registration, but you can wait and see what the weather's like because they don't fill up. So the only thing that might fill up is the male bunk bed, but if you're going to camp, I'm sure they won't fill up. And if you're a woman, they won't fill up the bunks. So you can wait and see what the weather's like and decide whether to do that one. Same thing for the York County Star Party. That's a very low-key one. There's no food vendors or rigmarole or talks, but it's a nice Bortle 4-ish site, only an hour and a half away. Good place to meet people. And Mega Meet is run by the Lehigh Valley Amateur Astronomers. That's on their private grounds. So you definitely need to register there, but even though it's the club's star party, they welcome anyone who is a member of a regional club. You just have to let them know you're coming. So that's another opportunity, and that's pretty close to probably maybe an hour away, I think. Yeah. And also, don't forget the public star parties at Valley Forge. The next ones are July 6th, August 2nd with the backup of the 3rd, and August 30th with the backup of the 31st. And we are looking for captains for the August 2nd and August 30th star parties. And what it means to be a captain is, first of all, you should have already been there once. So don't do it. Don't be a captain if you've never been there. But all you need to do is plan to show up and be like the host, welcoming. We have welcoming people, but bring the permit that we need for the field and make the weather call with the help of our weather calls team to decide whether it'll be held or not. So it's not a big job, but we do like to spread the wealth, get other people to help. So it's not always the same people. So if you have been to a Valley Forge Star Party before, you're probably qualified to be captain. So there's a sign-up sheet back there on the table. Okay, now we need to congratulate our new junior board member, and I see him hiding in the back there. Stand up, Daniel, so they can see who you are. So Daniel's been a member since 2021. He's a rising 12th grader at the Episcopal Academy. Last year, he won first place in the DVAA Youth Awards. And this year he won second place, in the Astronomical League Imaging Awards, both last year and this year. He founded the school's astronomy club, and he hosts star parties and meetings. And he's done astronomical outreach through a nonprofit called Astronomy for Equity. So we welcome Daniel, and I think it's going to be great to have his input into the activities of the club. Thank you very much for your interest, Daniel. We're going to put you to work. And also many, many thanks to Sylvie Stoneberg for her service as last year's junior board member. You'll probably remember Sylvie. She's given some absolutely wonderful talks and has helped us out at outreach and clinics. And we hope we can still keep her busy doing those things. Okay, we got a few reports welcoming from Brian Lee.
I'm Brian Lee, the welcoming chair. We have 5 new members and 1 returning member this month. George Wilkie, Cindy Callens, Leo Cohen, Claire Lynch, Emily Zimmerman, and the returning member is Gary Fick. So is there anybody here tonight? I didn't see anybody. I think so. Well, let's welcome them.
Is anybody here for the first time tonight, by the way? Oh, nobody. Okay. All right, now I'd like to welcome Tom, who's going to give us an update on DVAA merchandise. We've all been waiting.
Merchandising. And we're still waiting. No. So the store has closed. The order has been placed, and I'm told it should be ready in about 2 to 3 weeks. So all the merchandise will be here next month at the July meeting. So if you've ordered something, please come and pick it up so I don't have to lug it back and forth for too many months. And if not, if you can't make that, then if you are going to be at the Valley Forge to pick up, if you're going for the Star Party, and if you can't make the meeting next month, then let me know and I'll bring your stuff with me, and we can get it to you at Valley Forge. Anyway, so next month we should all be wearing our merch.
Thank you, Tom. And this was a huge amount of work to organize this. So great job. Thank you very much. Anyone else have any announcements they'd like to make? Okay. Well, I'd like to congratulate Iftikhar Taruno, as he is our first place winner for the 2025 Youth Awards. And I'd like to invite him up to give his presentation. It's on detecting solar flares within low mass stars using machine learning. And Al, who has championed this program, Al Lamperti, But sorry he can't be here. He had a grandson graduation to attend in Seattle, so I'm his stand-in. Okay, let's get you a mic.
Clicker too.
So my project was on detecting solar flares within low mass stars using machine learning. It says low mass stars, but it's pretty applicable to almost every main sequence star. And I particularly like this project a lot because it gave me a lot of room to expand after each advancement. And I feel like it's very useful to the Astronomical Society in terms of how much it contributes to research, particularly with other stars and exoplanet habitability. So to start off, stellar flares are intense sudden outbursts of energy on the surface of stars. And they're caused by another phenomenon that's known as magnetic reconnection. So magnetic reconnection happens when cross-magnetic fields on a star snap, and this causes it to explosively fling away particles at high speed, and it releases a lot of energy, which we from Earth see as a stellar flare. So I have a video here showcasing how that works.
I can't do it. Looks like it's on Google Drive and I don't have access to it. No, sorry. No, it's because it's remote and I can't access it.
So this was just a video demonstration of how stellar flares work. But basically what happens is when you have these magnetic field lines and when they snap, it basically causes the charged up particles to fling away. And that's all this video is. My research question was how effective machine learning methods would be in detecting solar flares. So obviously for stars that are very far away, having a system that automatically detects and captures these solar flares would be very useful. And I wanted to do that with the new AI machine learning models that are very useful in the field nowadays. And my hypothesis was if it is possible to detect solar flares, it could provide an efficient and accurate way to detect solar flares within low mass stars that would otherwise go undocumented or undetected. So the tools I used was the MASS Barbara Mikulski archive for space telescopes. This holds a lot of astronomical data in a lot of different areas. I used it particularly for solar flare data and what is known as light curve data. Light curve data is basically the brightness changes on the surface of stars, and satellites basically capture that, and they have it out as open source data that you can use for any research that you'd like. And after you download this data, I had to do something known as a flattening.
You can use the laser pointer.
Yeah, is it working?
Other way around.
Oh, sorry. Yeah, I used a flattening procedure, which basically made it so that all this data that I got, I could turn it into something where I could easily see when these flares happen through the peaks, and I'll get more into that in a little bit. For my machine learning model, I used PyCharm. This is a free to use scripting language. It works with Python, and I used this program to write all my machine learning scripts and my code. For my procedure, so when you initially download the data from the website, you would get stuff that looks like this. So the TICID is all the different stars. So for example, this is TICID 364588501. This is a very I use this for a lot of my testing, and it's a very well-known star in terms of stellar flare detection because its peaks are pretty easy to see, and it's used a lot in the field when testing how well a certain procedure is doing in terms of stellar flare detection. So when you initially download the data, it all looks like this. You can see that some of them have little to no noise, whereas other ones have a lot of noise. So this is how you download it, but you need some way to see these actual peaks. So what you do is you do a flattening process where you basically flatten the data down so that it's easier to see these little peaks, which could be candidates for stellar flare. And you can see how they vary from all the different stars. Also, sectors are specific areas of the star. Obviously, the satellite can't map the entire star at once, so they split it up into sectors, and that's how you can get more data for your model. So, as you can see, we can see these peaks, but we need some way to communicate that to a machine learning model so they can get the data so it can actually train itself to be able to detect more flares in the future. So what you have to do is you have to break down this graph into numerical data. And what I did for that was for a particular peak. So as you can see, this was a peak that went pretty far from the standard deviation line. And what you ideally look for in a flare is a rapid rise and then a slower decay. If it's a rapid rise and also a rapid decay, then usually we don't count that as a stellar flare. So the three main features that I counted for a particular flare is the duration of the actual flare. So obviously, if it's like a quick rise and then a quick decay, then obviously, like I mentioned before, it's not a flare. So what my model would basically do is it would check for a particular flare if it went off the standard deviation line, check how long it went off the deviation line for, and then it would also check how long it took to actually reach its peak, and then how long it took to reach back to the standard line. And that was another feature. And then the final feature is how much this peak was compared to the standard deviation line. So how much higher this peak was compared to the standard one.
What are the time units?
BTJD.
What is it?
BTJD.
Could you explain that?
It's before Julian date, I'm pretty sure. It's how the satellite calculates the time for a given star. It's a pretty standard unit in this.
Those are days then, right? At the bottom of the
Yeah,
days.
days. So after you do this procedure, you get all this data, and I had a separate set for training data and a separate set for testing data. Basically, I wanted to train the model first on some of the data on flares that we know about, and then I want to see if it could calculate some other flares to see how well the model is performing. So after you do this procedure of breaking it down, you get all this numerical data that you can feed into the machine learning model. So for my training, I worked with these stars. I chose these stars because they're all very different. Some of them are larger, some of them are smaller. Some of them have more brightness variations compared to usual. So, and they're also used by the most recent study, which also tackled stellar flare detection with machine learning method. I wanted to compare how well my model would do compared to theirs. So these are all the different stars, and that's all the sectors. So here's a picture of all the different stars. You can see that some of them are in binary systems, like the one over here. Some of them are larger, some of them are brighter. And then the one in the top right here is what's known as a eruptive variable star. It's notable because it has more frequent brightness variations compared to usual. And I added this one because I wanted to make my model more general so that it could tackle almost any stars and it wouldn't be just stars that have normal brightness variation. So I wanted to make this model very general so that you can use it on many different kinds of stars. So moving on, for my actual machine learning model, I had a lot of choices to pick from, but I picked the ones that I believe would best tackle the data that I have. So the first one that I used was a random forest classifier. This is pretty popular in the machine learning in machine learning because it can do flare detections and classifications on almost any kind of data that you have. And some of the advantages that it has is that it reduces overfitting, handles high dimensionality, and is robust to noise and outliers, which my data has. How it works is basically you train what's known as trees. You basically feed into the model data and it tries to find a pattern between how the numbers match up to an actual flare detection. And it tries to find, and it trains all these different trees that all individually learn different patterns and tries to find which trees are performing the best. And it builds upon itself to do better and better on itself. The next model that I used was XGBoost. So compared to the random forest model where you're training all these different trees, an XGBoost model actually creates a tree, trains itself, checks its accuracy, and then for the next tree that it creates, it learns from itself so that the next tree is better than the last. And this is helpful because it has high performance, scalability, and flexibility. So it's not just for a single kind of data, you can train it on multiple different kinds. And as you can see, these have some disadvantages as well. So I wanted to reduce the disadvantages, and what I came up with was a multi-algorithmic model. So a model that would use both the random forest model and the XGBoost model so that you can have this agreement factor where if one model is saying something is a flare and the other one is saying it's not a flare, you could check which model is performing better so that if both say that it's a flare, then you can know for sure that it's a flare. So I worked towards that. And what this allows is to leverage the strengths of both algorithms and its complementary strengths. So as you saw before, each of them have different advantages and disadvantages, and I wanted to utilize that and create a better model. That would leverage the best of both worlds. Another point to consider is why I didn't use other models. For example, another popular model is convolutional neural network, but that's not that didn't work well here because of the low amount of features that I have. Like I mentioned before, I only used 3 features here. So if I had more features, I could use the convolutional neural network because it works better when you have more data. So, and then moving on to results, what I got were really good. So compared to the study that I compared to, I had results that were almost 99% to 100% accurate. This is because of how well my feature distinctions were, because basically, like I mentioned before, you want to have peaks that fast rises and slow decay. So with the features that I used, it was really easy for the model to be able to detect those. And for what I was testing against, so to know if what I say is a peak is an actual peak, I used a popular study, and they're scientists that have worked on this in the past. So I was able to use their true data to make sure that I was actually classifying a flare that scientists have noted as a true flare in the past. And as you can see, you might think that the multi-algorithmic model performed worse than the XGBoost model. As you can see that there's 99%, whereas all this is 100%. But as I mentioned before, because of the agreement factor between the two models, I believe that's more useful than just having a model that would classify them all as true. And then I tested this in all these different stars. And compared to that one study, I was able to properly detect 906 of their flares within my model as well, and also detect around 7,000 more flares compared to that. And you can see all the different flares I calculated for each of the different stars. And then outside of just predicting flares, I wanted a more accurate model of actually forecasting flares. So not only would you be able to calculate all the flares that have happened in the past, but you'd also be able to calculate flares that might happen in the future. So what I did was I trained a forecasting model. What this basically does is for all the flares that have happened on a given star in the past, it would break it up into seasons, where depending on the rotation period of the star, when the most flares are happening and when the least flares are happening, and on which sectors they're happening. So this would allow you to forecast flares and document them for all future studies. And as you can see, it gives this forecasting model gives a current probability, and it also gives a running model on what the percent is of a flare happening currently, and of when it will happen again in its next 7 days of its rotation period. And it can vary, obviously, because some stars have more frequent flares and some stars have less frequent flares. I had another video demonstration, but obviously it won't work. But
You can try it if the permissions are better on this one.
Try.
No, it's like the same issue.
Yeah. So what this video demonstration was going to show is that I put together all that I mentioned before, and I actually created an application. And this application would allow you to basically, if you're doing any work with stellar flares, you would be able to find all the flares that have happened on that given star. And you can use that for your own research. And if you want to work with any flares that might happen on the star in the future, you can also find that with the forecasting model. So this would be a very robust application for the scientific community. And I wanted to make this open source and eventually publish it as a website that for anyone that wants to do any work with any star in the future, they could easily gather all the data here instead of doing the procedure of downloading it and then manually finding all the flares on their own. And so in conclusion, the machine learning models were extremely effective at detecting stellar flares, not only on low mass stars, but also on almost all main sequence stars. It's a very powerful and robust model that leverages the best of both worlds, like I mentioned before. And it records the flares for documentation. So on my actual application, every time it finds a new flare, it will actually save it to the system so that the next time you run the model on the star, it would already have all the detected flares saved, so it won't take as long. So as we run this model over and over again for all the different stars, you'll actually have a complete catalog of every flare that will happen and might happen in the future. So it's very, very useful. And again, it shows all the flares that have happened, might happen, and are occurring right now with its forecasting model. And if you were to connect this to like a satellite that's actually collecting this likeness variation data, you can actually get live stellar flare detection on all these different stars. So it's very versatile in its applications. Detecting and documenting stellar flare is crucial for understanding stellar magnetic activity and also exoplanet habitability. So exoplanets are a big thing in the scientific community right now because they basically tell you how well other planets are for human habitation. And a main thing about that is where if the atmosphere of the actual exoplanet is suitable for humans. And a main thing about that is its host star. If the host star has a lot of strong solar flares, that makes the atmosphere of the exoplanet uninhabitable. So this is very useful in that area, and also teaches you about star behavior and learning more about our own sun as well. So this complete catalog of stellar flares is extremely valuable, and it's a vital improvement to what we have right now in terms of stellar flare detection. Thank you very much.
Have a few questions. You want to take a few questions? Anybody have some questions?
Why are low mass stars more prone to stellar flares than larger ones?
That has to do with the stellar rotation period. Low mass stars typically tend to spin faster compared to higher mass stars. So that's the main reason. And because the low mass stars spin faster, that causes them to have more magnetic activity. And since stellar flares are caused by magnetic reconnections, that causes them to have more stellar flares.
Which instruments generated the original data that you're using?
The flare data? I think the Mass Telescope did that. They have a location in the US that calculates all the flare data.
And what's the most distant star that you can detect flares?
Ooh, that would be depending on how far, depending on the satellite itself. I'm not sure what's the most distant one that I calculated on, but I would have to check.
Good question.
Yes, so many of the low mass stars are actually much older. And as stars age, they slow their rotation. So how do you come up with that? You know, why would we expect that these low mass stars would still be spinning much faster if they're over time they are actually slowing their rotation?
Yeah, but not all stars fit into that criteria, I'm pretty sure, because just because a star is low on mass, it could actually be closer to us. So it's not, you can't actually conclude that they're always older compared to like the bigger one. For the ones that I tackled, they were almost always, they almost always fit into the criteria of having a lower rotation period, and then having more flares. If I could pull up the data, but that's the general trend that I found, that as these stars had a smaller rotation period, it caused them to have more flares. That's the trend that I found.
Okay.
Yeah, machine learning technology that you use, is that something that's only been developed in the last 5 years or so?
It's definitely become more popular in the field of astronomy in the past 5 years. With more advanced AI systems nowadays, a lot of people are utilizing these machine learning methods to automate a lot of the processes that were usually done by humans. And stellar flares is a particular one that's new to that.
Okay, we have one more question over here.
By the way, this is awesome. I was really impressed the second you said that you use Python, because I'm like a big fan of JetBrains, and I was like, way to go. And what I need to ask you is, how many hours of coding did you do, and did you use MATLAB at all as well in what you did?
Yes, I think for the graphs that I showed you, I used MATLAB to create those. In terms of hours, it took, I believe I started this back in like November in terms of just researching it. And then over time, obviously, I had to learn a lot of the machine